Hi guys. I guess we'll just get started here. Welcome again to another Common Lisp study group. Today we're going to be discussing Chapter 13, which is sort of it's finishing up the discussion on data structures in Common Lisp, in particular beyond things that you can actually do with concells and the list structure itself. We sort of started on this in the last episode when I started giving a discussion about concells giving you the ability to make arbitrary data structures such as trees. And in fact, trees are you could essentially think of like lists of lists has trees, and it's mentioned in the book on how the structure is kind of shared amongst the trees. Common Lisp has a couple of nice functions to deal with trees. If we actually go through, I have like a nice little example here of a simple tree. The design of the tree that was like mentioned in the book, it just to give you guys a little bit of a sort of I'm going to just show you this guy. If you look at the tree structure example that was mentioned in this chapter, we have essentially the ability. We start with the list of essentially a list of lists here, which behind the scenes will actually just end up becoming a tree-like structure because the console, again, as we mentioned in the last episode, is essentially a data structure of two pointers. One that points to the car of the list, and the other points to the caterer, or the first or the rest. Because this is a list of pointers, you can think of these sublists here, like in the example that Peter provides, 1, 2, as being a pointer to another list that whose first term is 1 and second is 2 and so forth. So these are all like subtrees almost that you could think of. To really bring this home, I thought it would be great to show a couple of examples that I made myself, and to bring that in, let's go to my Emacs editor, and I created one here as well, which is essentially two subtrees. And if you think about it, it is the first subtree has essentially a 1 on the left-hand side, on the left child, a 2 has being the root of another subtree with 3 and 4 has its children. And the same thing on this other side, it will be 5 has the left child, and then 6 has the right subtree, but it's a root of a right subtree that has children 7 and 8. You have these nice convenience functions in Common Lisp to mess with trees. Just to show you, if you type in tree and do a meta tab, you have something called tree equals that you could take in, one tree and another tree. You specify a function has a testing function. By default, it's just equal, and it will go through each element and check if the two trees are equal. Additionally, they also have something called copy tree that actually copies the tree atomically. That means it doesn't actually share the structure for the same structure like you would in list. Instead, it will actually take each cons cell and make a new cons out of that cell, essentially constructing the entire tree independent of these things. And to show that, I thought I would show off a couple of these other convenience functions that you could use to implement that you could use on trees. Common Lisp in particular has the exact equivalent exact tree equivalent has the list function. So like if you remember when we were talking about lists, they have things like substitute, substitute if not. Well, in Common Lisp, the tree manipulation functions are exactly the same way. So if you have substitute for a list, then if you want to do substitute on trees, you just use just take out the etute, and you have your the substitute for trees. To give you an example that this is a functional substitute, if we simply copy the tree in here, in this first example, we are copying the tree and we're just simply taking and replacing 2 with the value 10. If we run this guy, oops, I apologize. I have to first find it. If we run this piece of code and we see what happens in the REPL, you will see that substitute didn't actually modify the copy of the tree itself. Well, that's because substitute is does not actually modify the original data structure that's passed in. It's a functional version of the recycling version, which is called end substitute. So if we go in and change this guy to end substitute, which goes and modifies the existing structure, and we run this again, you'll see that the tree structure did get actually modified. But did the original get modified? Well, no, it did not. If we could just simply run a print on this, and if we run it, you'll see that the original data structure that we copied from did not get modified. This sort of should show you that that behind the scenes Lisp system is not sharing any sort of structure between the original tree and the copy itself. I know this will get some getting used to, but essentially, like we said before, there are the functional versions of doing copying some stuff and the recycling version. So like the shared structure versions of doing copying and the non-shared structure versions. And in the case of trees, there are atomic versions of these where you can get completely independent deep copies of data structures, in particular trees in this case. Not only can you substitute values in the case that I showed you, in this example, I'm taking a tree essentially of dotted pairs, which we'll talk about later. It's in a little more detail. And this guy actually passes in essentially a structure and says, if you find a subtree of this type, just highlight this guy. Oh, sorry, it's if you find a structure of this type, which essentially is a dotted pair with old and pair, what it will do behind the scenes, it'll replace it with the a.con. So let's see how this works. If I run this, and if you see, can you guys see my mini buffer? Michael, Judd, can you guys see my mini buffer?
Yep.
Okay, sweet. Just want to make sure. You will notice that the old dot pair, when we evaluate this, has been replaced with a.cons, and the sub function allows you to specify. It gives you the ability to specify a subtree pattern, and you can actually completely match that pattern, and then it will it'll replace it. Just like lists having substitute if not, remove if not, so forth, trees have, and the substitution functions in particular have the same like if and if not. So in this case here, what I'm doing is I'm taking a copy of my tree example, looking for the specific subtree 1, 2, 3, 4, and it will actually replace that with an X. All right. So when we run this, you'll see in the REPL, since I'm printing out the result, that entire subtree has now essentially been replaced. Just a couple of manipulation functions that you can normally, you know, use on your day-to-day usage of common Lisp. I think it would be, you would probably end up using substitute if, and of course, the recycling version would be particularly useful if you really need to worry about like consing, because it does not cons. Just to show you, just to wrap this up here, on trees, the entire time, because I'm making a copy of this tree, the original tree has been unmodified. If I wanted to, I could certainly replace this guy, this end substitute, with tree example, and then, you know, just like what we showed you earlier, it will go ahead and it will modify the actual data structure. So if we just run this simple example here, and we print out the tree, you will certainly see that the subtree has been modified itself too as well. These are just simple simple things that you could do with common Lisp trees. Most certainly, there are other things you can do, but just to most often than not, you'll probably end up using. I would say you would end up using lists, vectors, and A-list and P-list for small stuff, and then more often even hash tables before you start dealing with like trees. But the trees is definitely has its uses in a lot of cases, depending upon the application that you're creating, just like any other basic data structure. There are things related to trees in terms of like performance things, but there isn't too much for me to discuss on that. I think it depends on the use case that you're doing and what you're leveraging trees for, as to what limitations you might end up coming due to potentially extra consing happening because of the copies that are happening around. Any questions?
Let me see. For the end substitute function.
Yeah.
A lot of the functions in Common Lisp, the destructive ones, say if you read the standard for them, they say that they may be modified. They may modify the original. As far as end substitute, it says that it will modify it, but the result may not be EQ.
Got it. Yeah, and that's a very good point, Michael. Thanks for bringing that up. Yeah, that's because of the extra consing or potentially non-extra consing, it may no longer be EQ with the
as far as like delete F or a lot of functions that destructively modify. Delete F specifically says that it might modify. You have to really look at the standard if you're doing destructive operations, because it might not work on all implementations of Common Lisp.
Interesting. That I read that in the standard, but I wasn't entirely sure what it meant by may or may not. So it might be. Are you saying that it's left to the implementation designer as to whether or not it?
Right. It's just not specified in the standard whether it's actually modified or not.
Okay.
So that's not the case with end substitute, though. End substitute says that it will modify the original tree, but it might not be equal as far as memory.
Right. And well, that makes sense, because you're potentially you're creating new concells, or you're.
I just wanted to bring that up because as far as destructive operations, it might not behave as you expect, but that's not the case with what you're talking about here with end substitute and end substitute if.
Gotcha. So a lot of the subtree operations are definitely are destructive, and they may not be equivalent due to just the consing structure on how concells are actually being concatenated into the new tree structure that's being resulted from that end substitute if, right? Okay, so I'm just going to bring this guy up because I think this is definitely a good point. So what Michael was talking about the standard, if you guys are interested in actually looking at the standard, as I think I've shown in previous episodes, you can get access to it directly from Slime. But Let me actually pull that up. That would be probably pretty useful for folks. Let's do this. Share a different screen. You know, I'm going to just share my entire desktop. That's probably be easier. Okay. Let me go and change this to Emacs, and let me go to, hold on, sorry. I apologize, folks, watching this. It's one of those things. All right. So like what Michael said earlier, N substitute is going to destructively replace everything, and this is straight up from the Common Lisp hyperspec, which you can get access to by running simply in Emacs. If you run slime hyperspace lookup, which has a key binding on it, but I don't remember it off the top of my head. You just simply
slime hyperspec lookup or just hyperspec lookup? I can never remember.
It's slime hyperspec lookup.
Okay.
So yeah, I mean, at least I remember slime. There might be a separate hyperspec lookup. I don't think there is. Oh, there is a hyperspec lookup too. So
yeah, because that's what I always use.
I know slime has a tendency for an equivalent for each of them, just so that it doesn't assume that it exists. So I always end up using slime's hyperspec lookup if I don't remember the key binding. So, but that's a good point. So you can use either or to actually get access to the Common Lisp hyperspec. This is actually, as you get more and more into the APIs, this will definitely become useful, especially when you're switching between different implementations, as Michael rightfully pointed out, Michael Piano.
Yeah, if you actually look up in the hyperspec N reverse and compare that with N substitute, a lot of the functions, the destructive functions in the hyperspec, actually look like N reverse, where it says the sequence might be destroyed.
Interesting.
The result might be identical.
Let me pull that up. N reverse.
N substitute, like I learned something new today. I thought that was the same as all the other ones because it actually says it will modify. It doesn't say it might like the other ones do.
Right, and I actually confirmed this when I was looking at this earlier today, but I didn't realize this last part that you pointed out, which is that the result may not be equivalent to the original tree that's passed in. So that's definitely new for me. You'll find all these gems as you keep going through the Common Lisp hyperspec. And it becomes more and more useful over time. I will say this, but again, has it states in the hyperspec, some of this behavior could be undefined. It's going to be up to the implementation designer has to decide what would be the best approach for their Lisp implementation. But you said, hold on, N reverse sequence might be destroyed or reused to produce result.
Keyword might.
Yeah, I see that. The result might or might not be identical. Gotcha. That's definitely that's new. That's new to me. I should keep that.
And a lot of them actually are worded like that. Delete F is another one that comes to mind. I mean,
sorry.
And N substitute is the only one I know about that says it actually will be modified.
So let me get back to what I was saying, what we were talking about earlier, which is so bottom line is you're gonna end up playing around with some of these convenience functions for trees. For the recycling things, I'm gonna be cautious and say try not to use them, but benchmark and see if you really need to use them, and then look up in the hyperspec to confirm what the behavior is of the particular recycling function that you're leveraging. to know what the differences are, so that you don't have any sort of like surprises as you're coding. So moving on to sets. So this might be surprising. It may not for some folks that are on the call, but you know, it might be surprising to others watching this. Sets in common Lisp is just basically lists, but there's a coinciding API that that you will have to leverage if you really want to have set semantics. So in this example here, we could create a set using just a simple empty list. And I'm just going to create a set with some elements in it. To check set membership or to add something if it doesn't exist, you can use a function called add join. But add join, by the way, will return the list or set with the element added to it. So what that means is if I print the actual set, you might think, oh, well, it's been added. Well, it hasn't actually, because we didn't actually do like a set F if we're going to use add join. If you wanted to actually, because this set F, now one set join, one set, you can see here that this guy now has one in it. This is so common that you can use something called push new, which will do the same thing. Like in this case, if I try to add one set, one into the already existing set because it's been added, you'll clearly see that it hasn't been added when you use push new. You can add a couple of elements into here, and then you'll see that they'll just get ordered in reverse order. It's not in the order at which you've been added. It's not appended to the end of the list. It's actually pushed onto the actual set itself. Once you have a couple of sets like this, you can use set operations just like normal operations. And Common Lisp has your standard set union. It has your set intersection, which will take in two sets and gives you what commons in both sets. It also has set difference, which will return the values that are in A that are not in B if A and B are two sets. So in this case, it will return 4. But if you reverse it, it will return what's in another set that's not in one set, which in this case, it's 3. Additionally, there's one more operation that Common Lisp provides, and that's set exclusive OR. What that does is it returns a set of elements that are in either or set, but not in both. So if you recall, one set has 4, 2, 1, and if we print out another set, we'll see that it has 1, 2, 3. So the set exclusive OR from this should be what's in both either in one set or another set, but not both, which should be 3, 4. And as you can see, it actually is in 3, 4. These will come in use, very useful when you're doing, your standard set operations. Don't believe the book talks about complements, but I think you can. Is there a complement, a set complement in the Common Lisp API? I don't think so, right? I doubt it.
What do you mean by set complement?
Like, I guess, actually, that's a very good question.
Right.
Mathematically.
Instead of all things.
Yeah, that's right.
Except these ones. Good luck representing it as a linked list.
That's a very good point. I just was like, wait a second. It has everything, but complements. They're complements. Well, I guess you don't need complements because that's everything. Everything is a complement of whatever is not in there. So set membership. You have a function called member that essentially checks to see if something's in a set. But what you think it's going to return is not a true or nil. What Common Lisp returns is actually the con cell that contains the value, which really is like the sublist. So if you have, multiple, as you saw here earlier, multiple elements in the set, and you check to see if any of them is in a member is a member of that set, it'll return the sublist that's containing that value. So if I run this, I thought I'd show you this by iterating through one of the one sets and do a member on it. Let me actually load this guy up just a little bit. Okay. So when we run this piece of code here, you will notice that, as it's iterating through the set, it's giving you the sublist that includes the actual elements. So the first thing is doing a member of 4 in one set, which means it's going to give you the entire set, as you saw earlier. Second one is going through 2, which means it's going to just give you 2 in 1, and so forth. You could certainly use this to use memberships, because if you just do if member or not, it'll print out the truth value correctly. But just to show you that it will return nil if you don't have it in this set, I'm just going to run this simple example, which is testing if 5 is in that set, which it's clearly not. It'll return nil. You have, again, like everything else, you have member if not. So in this example, we're testing and finding the sublist that contains at least one number, and it will return that sublist that has at least one number in it, and it's returning 23B. Associative lists and property lists. I know I'm going pretty quickly here. Are there? This should be pretty straightforward. Are there questions though, or is any comments that of stuff that I'm talking about here right now? Okay. A-lists are basically just lists of consoles, or dotted pairs. Really, they're dotted pairs. So to show you what an A-list is, I gave an example here, how it's structured here. We're creating something called star A-list. If we wanted to check its association, we could do something called ASOC, which I'll show later. To add things to the A-list, you can do cons, and you could specify a new cons cell here, and then add it to the beginning of the list. You can also technically also add it to the end, but I'm showing you the beginning of the list for a certain reason. There's a convenience function that actually leverages that. This guy here, if you run this by itself, you will notice that if we tried to print the list, it didn't actually add that new value. That's because cons does not actually modify the current list structure. You have to use set f. So if we actually do this here, we'll get it properly added into the list. As I mentioned before, there's something called acons, which will add values into associative lists like this. And just to show you what its parameters are, it'll take in the key first, then the value, and then the actual associative list that you're going to be modifying. Again, acons does what I showed you in the cons example earlier. It does not modify the actual list. You're going to have to actually set f, the actual associative list, to add new values, and it'll print that list out. To use to check if a particular value is available, you can use ASOC to check the associativity with a particular associative list. So in this case, I'm checking to see if A is there in the A list, and if that is, it will return it. And what it will return is the dotted pair. It will actually return the cons cell that contains the key A and its value. If it doesn't exist, it will return nil. By default, and this is something that's particularly interesting and definitely useful for folks who are just starting off here, the key of an associative list that is in the list of dotted pairs is always going to be a symbol. It's going to be a something that uses a quote and this value here. Or you can actually, there's other ways to create symbols in Common Lisp that I won't touch base here, but the key, the bottom line is the default is always going to be some sort of symbol. And the reason for, if you're going to use, like, say, like, a string for the keys, of an associative list, like in this example here? Well, in that case, what you're going to end up doing is you can actually set the test value. So if you look at a lot of these set membership functions and these other structures, this is just a common thing in all of Common Lisp. You have these additional key parameters. The key is like the default. If the structure has some ability for you to return the key, you can certainly do so. You have a test value, and that's testing the positivity, and you have a test not, and we'll just do the negation. In this case, what I'm doing is I'm replacing what originally was the test function, which is EQL by default if you're using ASOC, with string equals. And what this is does case sensitive string comparison with the car of the list. And if we print this out, you will see certainly that it will return the dotted pair that contains that key value pair. This I know we'll get some getting used to, just because I think in other languages that support pseudo associative lists, right now I can only think of, I think, like Python. You can actually mimic this with like dictionaries. You would almost always end up, or list itself, you most always end up being able to do a strict string comparison that way. This is a little different in how it's representing it, but the convenience functions all have these optional like keyword parameters that you could leverage to change the behavior of the underlying function. And you can certainly use that to your advantage if and when you need to use it. Key lists are kind of like associative lists a little bit, but they're more stringent in that the lookup of plist is almost always linear. So if you do, you have to use particularly something called getF to actually get a particular key value pair from a list. So if we do, in here I do A1, B2, C3. This is how you would create a basic plist, and the structure of the plist is key first, then value, key first, then value. If you want to leverage getF, you can actually do this on plist. And if we leverage that, oops, I messed that up.
I always mess that up.
Indicator, is that it?
It's deeply frustrating that the order of those switches around so often.
Yeah, it is deeply. Okay. Why is that not? Oh, so I have to do this.
Oh, your plist doesn't use keywords for its symbols.
Oh, shoot. All right. Thank you. I was wondering what the heck am I. There we go. I'm so used to setF I should remember getF and setF follow the same sort of semantics.
No, they don't. One of the I mean, you're right. It's that same ordering, but there's no relation between the two other than that.
Right. I'm talking about the function. I'm talking about the function signatures sort of match.
Sure.
Function name, the list structure name, and then do what you need to do.
Yeah, and they both take a place in their first argument, so I suppose. But still.
Yeah, this changing. I would have assumed that this would have been the right thing, but apparently it's not. So I'm just.
Yeah, it's how it is everywhere else.
Yeah. I'm just not.
There are a number of little backwards compatibility decisions defined in the making of Common Lisp that, you just sort of have to get used to.
Right. So to get something from a list, you have getF. You have something called remF to actually remove something from a plist. So if I do remF, I think it's star plist. run this guy, and then let's say I check to see if it exists, you'll see that it's been removed properly from the plist. You can use other types of things as your properties. You could use keywords, as I was trying to do earlier. So in this example, instead of, if I just did this, and I do get it, not printf. Sorry, I've been hacking C++ earlier today. I use a, you will see that you can actually leverage keywords as your key value pairs. Bottom line is this actually does a linear lookup, and I don't believe the other difference is in plist. Is it A-list that could do reverse lookup, or is one of them there was a way to do reverse lookup?
A-lists can do reverse lookup.
Yes, A-list can do reverse lookup. That's the other thing. Let's see. Reverse lookup.
Assoc.
Oh, Assoc. Thank you. Okay. So let me just go back to this guy here. Let me say if we do Assoc and do B A-list.
What is in that A-list?
That A-list should have had a.
What did you mean by reverse lookup?
You know, it's going to go and oh, sorry, it looks in the it looks at the values of. Right. I apologize.
Yeah.
Yeah, I'm messing stuff up here. So if you wanted to look A-list, hold on, let me just make sure I get it. Yeah, hold on. Down to, this is what I need to do. Yeah. So the difference between Assoc and Assoc is this guy looks at the car of each key value pair, and this Assoc looks at the decatur, or the value of the key value pair. So when it does the reverse lookup on it, it'll look at each of the values and then return the pair based on the value, not the actual key. So let's see, is there anything else in my notes that I need to leverage? Yeah. So the last thing that we will be discussing today, honestly, is just to deal with this thing is destructuring bind. We've shown earlier in other episodes about something called multiple value bind, and this is, the concept is a little similar, but what destructuring bind does is it allows you to specify a list of variables that you're going to be binding and a structure that is going to that's going to be either returned by a function or a form that you're passing in, and then you can leverage those values inside the list of forms that are encompassed around the destructuring bind. So in this example here, we're just simply grabbing XYZ from a static list that I just created here, and then we're just returning a property list that contains the key X, Y, and Z and their corresponding values. So when we run this, you will see in the mini buffer that the appropriate list is actually generated. This is kind of useful because a lot of functions in the APIs, especially I use this quite a bit when I'm like doing things with like sockets and socket programming, common Lisp. A lot of those functions return multiple values. I use either this one or multiple value bind to actually go and bind the return values to the particular values themselves. I don't believe, I know that there is a difference between multiple value bind and destructuring bind, but currently I don't remember the difference.
The difference is multiple value bind works with values, multiple values to be specific, and Destructuring Bind works with an arbitrary list.
Also, you can.
So you can't actually do.
No.
So
you can't put a value.
No.
Okay, gotcha.
Well, you could, but it would only work on the first value.
Right.
Okay. So this guy will not work at all.
That will try and that'll try and destructure 1 as a list of XYZ.
Gotcha.
And it'll get very confused because 1 is not a list. It'll probably actually tell you that. It'll probably say 1 is not a list.
Yeah, it will tell you that 1 is not a list. I'm now remembering this now.
Yeah.
But about Destructuring Bind, it actually can take as the lambda list argument pretty much almost any lambda list. It's called a destructuring lambda list if you want to be specific.
Yeah.
But if you change your like right where the if you do a p list there.
P list. Okay.
With keyword symbols.
All right.
Well, make one.
Make one.
A1, C2, C3.
And then you change the first argument, the lambda list part.
To start with ampersand key.
Yeah.
Okay.
And that'll just work.
And that will work.
Oh, right, because your keys.
So I have to change this to ABC.
Oh yeah.
Okay. Right. Those do have to match, yes.
Okay.
And then you can get into nesting. Like A could actually be a list.
Yes.
Instead of just a symbol. I mean, they can be arbitrarily nested. They don't have to be like a normal function signature with that ampersand key.
Gotcha. So the destructuring bind literally is just flattening the structure to something that you can leverage.
It's kind of pattern matching, really, if you're familiar with that.
Exactly.
And so it actually supports just about anything you can stick. We've been talking about lambda lists. For anybody who isn't quite familiar with that terminology, it's the arguments list to a lambda or a macro or a function or such. Those are referred to as lambda lists. There are a few different kinds of them, but the basic thing is rest, key, optional. Those semantics all apply to destructuring bind. You can have optional things that get destructured. So yeah.
That's pretty interesting.
And anytime there's a variable, you can stick another pattern there because it's arbitrarily nestable. Although, yeah.
So if I did, I'm kind of curious now. If I did that. Then do this. Okay.
Yeah, that'll work.
That'll work, of course.
You might want to print that return value.
Yeah, I'm going to do that.
Actually, well, you can just print the list inside. Either way, it doesn't really matter.
This will work, I think, right?
Yeah, it'll work either way.
Yeah.
And then you can actually destructure that 1, 2, 3, 4 if you want.
Right. Yes. That's the cool thing.
You can keep drilling down and.
So I could do something like
what you want to do.
Yeah. So this will give you a way of doing like flattening a little bit, in a sense.
In a sense.
One can actually implement flatten this way.
For a static
structure. Yeah. For a static structure, I should be very specific about that.
It's destructuring.
Right. All right. Hold on. What did I do? Oh.
Right. Let me think.
Destructuring bind.
Oh, right. Because it's a key arg. You need to wrap that in an extra pair of parens. Right? Because think about it. For a key arg, if you have a list in the place where it's expecting a key argument, it's expecting a list of variable optional value supply parameter.
I should do I guess.
No.
Just wrap it in an extra pair of parens.
FG.
Yes.
All right, like that. Okay.
Yes, like that.
That's not going to work either.
No.
Really?
It didn't work.
Why not? Oh, right, because you need to give Oh wow! I always forget that destructuring and key args works that funkily. You need. Yeah, let's not get into that. You can. I'm pretty sure you can actually do that, but it gets really funny. I should probably look at the formal syntax for that real fast.
Yeah.
Because that's all very formally specified where you're allowed to stick a thing there. Right.
So you can actually do. Let me see.
A better example would just be to get rid of the D in your P list with the 1, 2, 3, 4.
Yeah, hold on. Oh, hold on. Yeah, that you're telling me to get rid of this guy.
And also the D, E, F, G.
Yeah, got it.
And then wrap the ampersand key all the way up to the C in another list.
Ampersand key.
Just put double parens around everything there.
Okay, gotcha. Up, this, and this. All right.
And now you can do a list of lists for your value. Just put another paren after the quote.
Oh, okay, gotcha. Okay.
All the way up to the end of that list. Another one. No. Just put another open paren after the quote.
Oh, okay.
After the quote at the beginning.
After the quote. Sorry. You're talking about like this.
Nope. Go all the way to the quote, all the way over to the left. Put an open paren there.
Okay.
And another.
Oh, I see it now. You're saying like this.
Nope. Just another closed paren at the end. Okay. And now you can either work. If you move the cursor to the open paren ampersand key right there.
Open paren ampersand key. You're talking about right here. Gotcha.
Yep. Now you can put like, I don't know, Z.
Gotcha. Hold on.
Before the open paren though.
For the open paren.
Yep.
Oh, gotcha. This one. Okay.
Yep. And now you can do the same thing in your value form. Like make it.
Say 5.
5. Yep.
Then I can just do that.
It gets really messy when you start combining at rest and at key. So we're just working from the other side of the list.
So I'm kind of curious, have you ever encountered the use of the whole parameter? Because this was mentioned in the book too, and I wasn't sure about I've never actually...
I'm not sure if whole works for... See, these are called destructuring lambda lists. I'm not sure if they work there.
I don't know.
They're different from the normal... They're called ordinary lambda lists.
You can use whole in a destructuring lambda list. Yeah. I don't generally use whole a whole lot. But it is occasionally useful in writing very particular kinds of macros to be able to just get access to the entire. Because by the way, a macro argument list is very, very similar to a destructuring lambda list, and you can actually do the same kind of pattern matching there. But very occasionally, it's really useful to get access to the entire form in a as part of a macro and when you're working with a macro.
Oops, sorry.
Like there's some. Well, let's not go into why you would need that, because that starts talking about complicated things like compiler macros and nonsense.
we're not at that stage just yet.
We're not. Hopefully we'll get there soon enough, but there are places where you want to get access to the original form that was passed into the macro, and so in that case you want to use whole for that.
So that's all I have to cover today. I'm sorry to make it so short. Life sort of got in the way, and I've been I prepared this like last week to get, and I thought we would have time last week to get through it, but it looks like we didn't get through it. So we finally finished through a basic overview of common Lisp, data structures that are available to you at your fingertips. There's a lot more I didn't go into, particularly like third-party libraries that are available and things like that, because all that will come in due time. We're just currently focusing on the core language. Are there questions amongst the people, like Michael Gargano? Do you have any questions at all, or? Okay, Judd, any comments? Stop. Let me stop presenting. All right.
Sorry. Yeah, I always have questions.
Go for it.
Yeah. Well, two things. They're a little, I don't know, maybe like off topic or advanced, but
no, go for it.
One question I always have is when people are implementing new like CL implementations. Are there any references aside from like the actual standard or like CLTL2 that people use to like maybe even like do subsets or examples of anything like that? Or is it just basically the raw documentation from the standard?
So I'll make one comment on that, and then I'll open the floor to other people. My own take on this is first off, don't use CLTL second edition, because there is stuff in there that didn't actually make the ANSI standard. Like, if you want to know what's actually in the ANSI standard, the best book I've read that gives a nice overview of it is Paul Graham's ANSI Common Lisp. Even that doesn't cover certain things like the series library that CLTL2 does cover. And I think Guy Steele's explanation of streams is a little bit better than Paul Graham's. But if you really want to know from an implementation standpoint, like what's available, I think the best source, like for implementers, for compiler, like that is compiler writers and other people who are interested in writing a Lisp implementation, the best source is the hyperspec, which we were showing earlier. That has a lot of details related to implementing Common Lisp. It's not an introductory piece like into writing a Lisp compiler for that. One recommendation I've gotten from other folks is read Christian Koenig's Lisp in Small Pieces.
Yes, that is a very good book.
And that's specific. I think Elijah could you speak a few words on that, because I think you probably read it.
Yeah, I've read a large part of it. I haven't gotten to the last couple of chapters just because, that's how things are sometimes.
Right.
But no, Lisp in Small Pieces basically walks you through defining the semantics of a scheme interpreter in a number of scheme evaluator. Sorry, let me step out of the whole interpreter versus compiler distinction, because that's not important when you're defining semantics. It defines the semantics of a scheme evaluator in a couple of different ways in terms of scheme itself, so implements it in scheme, in terms of functional programming sort of theory of programming language design, and then it actually starts getting into optimizing and generating actually C code, compiling to C from Lisp code. So if you're looking into sort of theory and ideas on the design of Lisp implementations, a good place to go is Lisp in Small Pieces. It really walks through a lot of those the ideas involved and the mindset involved, and it gets a little thick partway through when they start doing mathematical, theoretic, semantic definitions of how a scheme evaluator works. That was a lot of Greek symbols, quite literally a lot of Greek symbols. But altogether, very good book. Very good book. Yeah.
So one additional comment I will make about Lisp in Small Pieces, if you end up getting it, which I do recommend because it is on at least. It's a very good book to teach in general how to write like Lisps and like because of the design like principles that he went through. But on top of that, it was written in a form called, like I was mentioning earlier before we started this broadcast. But for those of you out in the digital world, you might be interested to know, it was written in a style called the Literate programming style, which I think many in the digital realm have probably touched in some way, shape, or form. It in particular combines documentation with the code design. That's the reason why a lot of what you were mentioning earlier, Elijah, about the mathematical foundation is available there. It's because he wanted to keep that design, that theory, in conjunction with the code examples. And in fact, if you actually extract all the code examples that are in Lisp in small pieces, you do have at the end of that book, once you've completed it, a fully functioning, or you should have a fully functioning scheme compiler that implements a good subset of R5RS, if I'm not mistaken. So I do recommend people who are interested in writing Lisps and Lisp implementations to go through that book. In fact, I think I read originally about that book when Rich Hickey was starting Clojure, because I vaguely recall one of the things that someone asked him, well, how'd you get into implementing, Lisps? And I do vaguely recall the discussion going back to that book, Lisp in Small Pieces. So that's really probably your best starting point, Michael, if you really want to get into that kind of stuff.
Okay, good to know. The other question, which kind of ties into that one, is like before PCL existed, what because that was probably around after, I guess, most of the people that are doing advanced Lisp in this group probably learned it before that.
Well, actually, quite a few of us learned it from PCL, to be honest.
Okay. But I was just going to wonder, like, what that kind of.
Yep, I've been doing it for about 10 years now, and I learned it from PCL. So I don't know what was before that.
I can go into that a little, actually, because I've kept a good eye on a lot of the other books. On Lisp is a pretty good one. So I mean, part of the trouble is that if you're looking very specifically at ANSI Common Lisp and an introductory book on that, PCL is probably the best one in a good while. On Lisp is a decent one as well, although it's a bit more advanced.
On Lisp is a good success for good.
Yes, I agree. But it was older. I mean, the thing is, like, nobody really was terribly interested in writing the very introductory level stuff, like, for a good while after ANSI Common Lisp was standardized. And so you'll find some good introductory books that cover that like are based in Common Lisp the language 1, right? Or something along those lines. And so they're good books and they're good introductions to the language, but they're also not ANSI Common Lisp. And so, like, you have to be aware of that when you're reading them.
Yeah. So I can go into a couple of books that I sort of stumbled on when I was going through it. There is, prior to Practical Common Lisp in 2005, if you wanted to learn Lisp, like you would want to have eventually you'd want to get a copy of ANSI Common Lisp by Paul Graham, which was published, actually, I think shortly after the standard came out, like almost within like a year after the standard came out, he published ANSI Common Lisp, along with his successor On Lisp, which gives a good introduction. Well, it gives a very good tutorial on designing and writing macros. But on top of those two books, you have also David Turetsky, who created a book called A Gentle Introduction Common Lisp. There was what's his name?
It's Peter Norvig's Paradigms.
Peter Norvig, yeah. You can use Paradigms of Artificial Intelligence Programming, Case Studies in Common Lisp. Now,
Very specifically that one, and not Artificial Intelligence: A Modern Approach, was sort of the recreation of that book, but in Python.
Right. Well, actually, that's not true.
Right. Yeah.
Originally, it was all pseudocode. Then he made it into Python code.
Right. Yeah. But yeah, the earlier one, which was Paradigms of Artificial Intelligence Programming Case Studies in Common Lisp, that's a good book. But that one, as I was mentioning before, that one's CLTL 1, which means it's for the most part just a subset of Common Lisp, but occasionally there are actual differences. A subset of ANSI Common Lisp, anyway.
I will say that even if you end up hitting certain brick walls, reading PAIP, Paradigms of Artificial Intelligence Programming, is a good education. A very good education.
It is a very good book.
If anything, it gives you a nice breadth of artificial intelligence and how it was, like, the history of AI all the way up until even machine learning, because there's stuff on neural networks, if I remember correctly, that's in there too as well. Although it focused quite a bit on planning and expert systems. In fact,
well, I mean, planning and expert systems were really Lisp's forte.
It's symbolic computation. I mean, at the end of the day, it's inferential learning, and that's symbolic computation, whether we like to say it or not.
Yeah.
But
another one, if you're willing to step a little outside the Common Lisp space, would of course be good old Structure and Interpretation of Computer Programs.
Right.
Which is always a good book, and I still recommend to people, but is not Common Lisp, it's Scheme, and a particular variation on Scheme. I forget exactly which Scheme that one is.
It's MIT Scheme, I think.
It's MIT. It's Dr. Scheme. It's MIT Scheme.
Right.
I will say, though, that if you learn SICP, which I think it might be interesting since it is available online, we might want to, just do something related to that.
ISICP, Interactive Structure and Interpretation of Computer Programs. It works for like the first 5 chapters. Yeah. It has interactive examples, and the formatting is decent. So that's a good walkthrough.
On top of that, there's also Hella Belson actually also published a classical mechanics book in that same regard. And it teaches you scheme and functional programming, and it teaches you physics. So both Hamiltonian and Lagrangian mechanics too. So it's a very good book. And that also is available online too as well if you guys are interested. But for Lisp specifically, I think it depends on which Lisp you talk about. Scheme, there's a bunch of books that are there's the Little Schemer, there's
Reason Schemer,
the Reason Schemer, there's but for Common Lisp, before PCL, a lot of them were sparse, and a lot of them had disjoint subsets of the Common Lisp standard.
Yeah.
And to be honest, outside of Anti-CL by Paul Graham, I wouldn't suggest any of the other ones because of the historical.
Yeah. I think a good part of it was just that, right around the time the standard was being finalized, there just wasn't really anybody interested in writing introductory books.
Yeah, this is something you must know, Michael. Like, around the time the ANSI standard came out, which is like 94, 95, the AI winter sort of like went into full swing, almost completely. A lot of folks ended up actually leveraging C++. Many folks actually started. This was around Java 1.1, Java 1.2. They started moving into that direction because there's another garbage collected language that was available. Although
Python was, starting to get known.
Yeah, and this was Python 1.5, close to Python 2. Right. So
close to Python 2.
Yeah, close to Python 2. So really, because of that crash, that massive crash, and the investment in artificial intelligence, Common Lisp ended up, sort of falling by the wayside.
That and a number of other little things.
Yeah, well, let's not get into the other little. Right. Well, I guess I think we're at a point where we could start discussing some of them, but really,
Yeah.
It's
the thing is, I don't think it's that important. I mean, it's important if you're interested in the history, and it's important if you care about avoiding making similar mistakes.
right.
But I think for understanding the language, other than some of the theories on why Lisp as a language sort of encourages the kind of people that need a lot more discipline to work in groups.
Yeah.
Other than that bit of interesting psychology, I don't know if there's a whole lot to really learn other than be careful who you put in charge of your companies, among other things. I mean, there's a lot of history and politics and stuff that you sort of get into when you start looking at that.
I always reference to folks, and I'm going to say this to folks out here, that if you guys are interested in common Lisps like evolution, I still believe that the best take on the common Lisp community still, even though it was published almost 25 years ago, is Richard Gabriel's Lisp, The Good News, the Bad News, and How to Win Big, which actually has his famous Worse is Better articles embedded into it.
Yeah.
So, and I believe a lot of folks should read that just to understand, Lisp can evolve.
Yeah. It's not something that I want to really point people who are just getting into the language at, because I don't know.
It depends on the individual, I guess.
Yeah, it's easy to cite poorly.
Oh yeah. I wholeheartedly agree to that that sentiment.
Yeah. It's easy to use that particular series of articles completely to take them completely the wrong way and cite them incorrectly. But they are very interesting if you take them right.
If you take them
they
right,
are important.
Yeah. There's some very good points in them if you can read them.
Yeah.
But does that answer your question? I mean, honestly, in terms of book recommendations, I almost tell everybody do not even go outside of ANSI-CL and on Lisp. I think you should ignore Paradigms of Artificial Intelligence Programming. The majority of major common Lisp books out there, in terms of learning the language, honestly, yeah.
At least pre PCL anyway.
Yeah. Pre PCL, I would say read them with caution, because they're subsets of the language, not the entire language.
Gotcha. Yeah, no, that answered my question.
On Lisp specifically, and let over Lambda too, are totally devoted to macros. So I would actually recommend learning the language before you jump to those two books.
Let over Lambda is post PCL, though, isn't it?
Yeah, it's
post 2008, I believe.
Yeah. Though, also a great book, and one I would recommend you read after On Lisp, and On Lisp after PCL.
Yeah, so the order should be really is PCL first, then On Lisp, then Let over Lambda, so you don't get overwhelmed. And I would stick anti-common Lisp just as a reference, because there's a chapter on symbols that I haven't seen at all until I touched that book, to be honest. And it was referenced in On Lisp when he started getting into macros around chapter 7.
Yeah, I went sorry. The order I went was PCL, then On Lisp, then Let over Lambda, and somewhere in there mixed in was structure and interpretation and ANSI Common Lisp. Somewhere I just sort of referenced and mixed those in.
Actually, Michael, you've been programming Common Lisp for 10 years. Could you provide some insight into a suggestion while we're on the subject?
As far as
reading order, or other book suggestions.
After PCL, I would actually recommend picking up a new book. It just came out about 2 years ago. The author Edie Whites actually describes it as a companion to PCL, and it's called Common Lisp Recipes, a Problem Solution Approach. I mean, it's awesome if you read PCL and then you just need to flip to a page to figure out how to do a certain thing. It's awesome. It just has little snippets, little recipes on how to do specific things in Common Lisp.
So, yeah, Michael Gargano, just to get to talk about Common Lisp recipes, because I completely forgot about that book until it was mentioned here. That book actually has everything in terms of like, you know, database access to, I think, writing mobile apps using the Common Lisp implementation Mocal. How to reference, you know, it has some good patterns for, I think, referencing like form function libraries, and a lot of great gems. Honestly, I can't I can't believe I forgot that book, because
I mean, to be fair,
it's one of my favorite books.
Yeah. I mean, to be fair, the conversation was pre-PCL.
Yeah.
But
yeah.
To be honest, Common Lisp recipes is basically, you know, it's what I read when I have some spare time and I need to find something to fill it. I turn to a random chapter in recipes and I just absorb that.
And you know, as we get into certain things, like especially like developing and debugging, like he has an entire chapter dedicated to like, well, you know, you guys have to understand certain things about Common Lisp's development style to get used to it to actually pick it up. And he goes through a pretty decent explanation on what image-based development is all about. So I recommend you look at that book, especially as we start, you know, wrapping up practical Common Lisp, because it's definitely a great successor and a great reference book just to have on hand when you want to do something and you're not entirely sure what the best approach is. So looks like we're closing in on 7 here, but so I think next time, chapter 14, we're going to be talking about the path file library and file IO. You know, and hopefully during this discussion we'll have Wilfredo on, because he's had he's had a lot of fun with dealing with path names in his projects with with libraries.
I'm gonna warn him about that.
So it's going to be great. And you know, meet us next time. 5:30 to 7 is our normal scheduled time for these study groups every Tuesday. Any announcements from the Game Jam end before we close up shop here, Michael?
Nothing new. I think there's about 12 people are registered so far. If you're planning on attending, just go ahead to the website and I will post that in the chat. And register. Let us know if you're participating. If you need any help, just talk to Ram or myself and we'll point you to the right direction.
Yeah, and one question regarding team involvement. When you register on the site, do we have to have a team already in mind, or would we be able to go back to like picking team? If we end up coming onto a team, do we have to go back to re-registering under that team name?
No, it really doesn't matter.
Okay.
There's no right or wrong answer there.
All right, cool. Well, keep joining. You know, until next time, keep hacking away on your Lisp, and we'll see you next time.
Bye then.
Thanks.